Hey, good morning. How are you doing? It's the last day of school for 2020, and I'm diligently working to be finished with next semester because it's going to be even harder to teach. Hey guys, sorry, I'm a nut today. We're going to look at acid-base titrations. I believe it's topic 8.5. Week from Christmas, something like that. COVID, pandemic, end of the semester, everything's going on. I'm a hot mess. I'm sorry I'm rambling on your time. Okay, acid-base titrations. Need to have a good conceptual understanding of what's going on. Totally gonna wing this. I'm just winging it and I hope it works. I hope it works. All right, let's do this. Acid-base titration. Get it on. Share the screen. Let's go. Excited. Love titrations. Screen mirroring. Do it. Last time I did this, it didn't work. Hopefully it works this time. Yay. We get to do acid-base titrations. Yeah. Okay. So you know what a titration is, right? We've talked about titrations. Yes, we have. So during the process of a titration, we often, sorry, I'd like to come down here to a blank piece of paper where I've written this. During the process of a titration, right, particularly an acid-base titration, we often measure the pH throughout the titration, okay? We're going to look at several different pH curves depending on what is the titrant. That means what is in the burette, right? And what is the analyte. So what Miss Murphy just said, I don't like that. I'm going to make it a flask because it's more appropriate. And that there is your analyte, okay? And it is what is being analyzed. And we can use the results of our pH versus volume of titrant added to determine the concentration of the analyte. Or we can go in any direction, right? So they can mix it up where you're actually given the concentration and maybe other things, and you have to figure out, well, what volume would have been added at that point. Okay, so what you see with my graph, and it's actually called a titration curve. I think that you could easily see why they call this a titration curve. It's curvy. Well, let's start with our pH down low, right? And what can we immediately tell from this? Well, we can tell that we have a very low pH to begin with. And as a matter of fact, right, you need to be sure, sometimes you have to draw your own curve. So if your pH, and you have to calculate your initial pH, so you would want to start that where it should be if you're provided an axis, right? You want to be mindful of your particular pH to begin with. Therefore, we know that our analyte is an acid. Okay. If the analyte was a base, well, then we would see that pH curve starting, obviously, somewhere up high, maybe 14, maybe 12, 10. It depends, right? So we'll do our acid in red. How about that? Or maybe not. And then, so in here, right, we've got our acid. It may be a weak acid, or it may be a strong acid. The curve will tell me. Okay. So let's go. Let's continue. And in here, we will have our titrant. For our sakes, thankfully, I'm glad, our titrant will always be strong. Okay, but the analyte might be a strong acid, a weak acid, strong base, or a weak base, where the titrant will always be a strong acid or a strong base. And as we add the titrant, right, then you've written your acid-base equations to the analyte. We see that the hydroxide, which is the strongest base that there is, grabs onto the hydrogens that are present, leaving, if it's a weak acid, the conjugate base behind. The conjugate base of a weak acid is a strong base. Or if it's a strong acid, such as HCl, and we're going to pretend this is strong today, right now. So ours is going to be a strong acid. So we'll make the assumption that it's HCl. I would, upon every drop of hydroxide, removes a hydrogen, thus leaving the chloride ion behind. Now, this is important that you understand this. This is the conceptual stuff. This is the conjugate base of a strong acid. What does that mean? Very poor basic properties, right? So what we know is that chloride ion will not participate in equilibrium with the hydrogen ion. He's not going to try to get him back from the water. He's going to give him away, walk away. I'm done with that guy. I don't want anything to do with it, right? So he's just going to be in the water, and that's going to make this easier. So we add the H, then we drop the OH, and when we begin removing H's from our flask, and as we do that, our pH gradually goes up, right? Because we're removing those H's. Our pH continues to gradually go up. All right, I'm going to change that way that looks a little bit. And, right, our pH is going up, our pH is going up, our pH is going up. Whoa, it begins to spike. Whoa. And there's kind of your curve, okay? Let's talk about the plots on this curve. Right here in the middle of the spike, and this is assumed to be a strong acid, strong base, right? And when that is the case, the middle of the curve, which will always be referred to as our equivalence point, I want you to ask yourself, what's equivalence? The equivalence point. Oh, okay, right. The H is equal to the OH. So there's no excess of either, okay? And that is going to occur for a strong acid, strong base reaction. That's going to occur at a pH of 7. So I said that sometimes I can tell what type of titration is occurring by looking at the curve. If the equivalence point occurs at 7, then I know that I have a strong acid, strong base titration. Okay, you need to know that. Okay, there's some other things we need to focus on here. Right here is a very important point on this curve, okay? And this is called the halfway point. All right? Now, if this is a strong acid and a strong base, does it produce a buffer system? No. No, remember, we need a weak acid and a weak base with a conjugate, with its conjugate, typically provided in the form of a salt, but not always, okay? So because this is a strong acid, strong base, I'm not going to say much else about this. Let's go look at a weak acid, weak base. Okay. No, well, we don't have weak acid, weak base. Let's look at a weak acid being titrated with a strong base. Okay. Now we've got a little bit more going on. We've already talked about some of the basic stuff. So we're going to elaborate on some other things. All right. Over here will be our pH. Down here will be our volume titrant added. Okay. I want you to recognize what's going on chemically so that you really understand the concept behind this and you don't get confused by the questions that can seem hard and make you think. Okay. There's my scenario. Remember up here, we're going to have hydroxide ions, very strong base. Let me get my head out of the way. All right. Down here, this time, we're going to have a weak acid. Remember, weak acids like to stay together. When this reaction occurs, we will have HF plus OH yields HOH plus F minus. All right. The product of this reaction, excuse me, unlike up above where it was chloride ion, is the conjugate base of a weak acid and therefore participates in equilibrium. And what that will do, and it shifts the pH. Okay, you've got to understand it more than that. So I'm going to try to continue to explain what I'm talking about. pH what? At the equivalence point. Okay, so we have the stoichiometry part, and then we have the equilibrium part kind of again. All right, so our pH, wherever we start over here, we know it's going to be below 7, right? We'll give this a 14. We'll give this a 7. We'll give this a 0. We may have to calculate where that starts. So, you know, I can blame myself for often just starting down here and realizing, no, pH was given to me at 3. I need to start at 3. Okay. So I'm guilty of doing that. So be mindful of that. So at this point, we've got, oh dear goodness gracious, we'll just get him back. At this point, we've got our weak acid, whatever the concentration is. Remember, it can have a very low pH, even though it's weak, if it's very concentrated. And right here, what do we have present? We've got HF only, right? This is times 0. No OH has been added. All right, so I'm adding OH. I'm adding OH. So what's happening? I'm losing some HF, but I'm forming some F. So you need to understand the relationship there. All right, at some point right about here, this is going to be called the halfway point. And what that means is half of the HF, my weak acid, has reacted. Okay, now just think logically. If half of it has reacted, and we had 2.0 moles of it, then therefore we must have added 1.0 mole of this, and we had none of that, remember? Therefore, one mole of our acid remains, and 1 mole of our conjugate base has been formed. So can you tell me what that means if I now have a solution. Oh, dear goodness gracious. If I now have a solution that contains equal amounts of weak acid and its conjugate base, what type of solution is that? It's a perfect buffer solution, right? At the halfway point, you must know this, the moles of weak acid is equal to the moles of the conjugate base. Therefore, we have a perfect buffer solution. And in fact, the pH is equal to the pKa. Okay? There you go. And the HF is equal to the F. And that's not really in terms of molarity. It probably would be because they're in the same volume. Okay, so it would be. Now, before the halfway point, what do we have excess of? We have HF is greater than F. And wouldn't that mean that the pH, moving myself all around here, that the pH would be less than the pKa? Remember, a lot of this is based off of the Henderson-Hasselbalch equation. Right? So there's a big play between pH and pKa and the ratio of the concentration of base to acid. All right? Okay. And if once we get to the halfway point, right, these are equal to each other, as we saw down here, 1 mole, 1 mole. And therefore, when we divide them, it's 1 log of 1 is 0. We have the pH equals the pKa at the halfway point. Past, beyond the halfway point, right? I don't need to go too far. I've got a curve that's about to go up. So let me move these words here. And let me get a different color so it's not too confusing. Right, this is beyond halfway point, but before the equivalence point. We see that HF has now become less than F. So the pH is greater than the pKa, right? Which is obvious, right? Where the pH is moving up, but the pKa has stayed right here. So I can use this to determine pHs and pKas and lots of things. It will pop up. All right, let's continue our curve. Let's get this guy out of the way. Put him right here. Let's get rid of that arrow. Okay, continue the curve. Get our blue. And now we're going to spike upwards. Actually, let me look at what's going on here. I've got a weak acid, strong base. So let me not spike upwards yet because my equivalence point will not be at 7. And I know that because of my weak acid, strong base. So I'm going to keep going and do it more like this. Okay. All right, guys. So my halfway point might not, maybe it's more like right here, right? Yeah, probably. Okay. Not to be concerned with. We're still, all the information is correct. It's just that that is now there. Okay. Now we still know that in the center of the spike, right, is where we get close to the equivalence point. So all HF has been neutralized. Only F remains. Okay. Well, look at our pH. It will be greater than 7. And you need to know why, right? And here's why. All right, F, this is why. This is why. Participates, F participates in equilibrium and shifts the pH at the equivalence point. So F is the only thing present, participates in equilibrium with water. F is a strong conjugate base. Ugh, stupid head. F is a strong conjugate base. F participates in equilibrium with water. At the equivalence point, only the fluoride ion is present, participates in equilibrium with water, causing the production of some excess hydroxide, therefore basic at equivalence point. I hope that you understand that. If not, watch it again. You need to be able to explain it, right? As I continue this titration and I'm adding hydroxide to a container that has no hydrofluoric acid, it just continues to build up hydroxide ions. And at that point, the hydroxide dominates the pH. But at the equivalence point, where there is assumed to be at a perfect equivalence point, there's no HF, only F, and then F goes into equilibrium with water. Remember, there's a fight over this. Water's going to win it. The equilibrium will lie to the left, but there will be a slight increase of hydroxide ions, causing that pH to increase at the equivalence point. Opposite scenario, we have a weak base in titration with a strong acid. All right, so draw your graph. And this time, right, we've got volume of titrant here. We've got the pH on the left. This time we are starting with a weak base, right? So our curve will be upside down, or rather it will start from the top. Whatever that pH is where you would start it. So we'll just assume it's a little below 14, okay? So let's have our strong acid here be hydrochloric. And we know that we're only concerned with the hydrogen ion there. Why do I have green? Let's have our analyte be ammonia NH3, okay? So what is the reaction? It is NH3 plus the hydrogen ion yields ammonium, all right? Or we could incorporate water. Let me show you how we would do that. NH3 plus H3O plus yields the ammonium ion plus water. All right, I kind of like that a little bit better today. Okay, this is not pretty. I'm really bothered by this crooked line right here. So if you don't mind, I'm just gonna make that, try to make that straighter. Yeah, it wasn't any straighter. All right, let's go like this. Okay, so let's start our titration, okay? And let's start drawing our curve. And we'll see that at the addition of titrant, our pH will begin to decrease, right? I'm not very good at drawing a backwards curve. I'll just be honest with you. It'll slowly decrease. I can't even draw this curve. I can't do it. Something like that. Just try to draw it. I'm going to try to draw it. Okay. I think I kind of messed it up right there. One more time, last curve. And then let's talk about the points in this curve. All right, I'm just going to leave it at that. Okay. No, one more. It needs to go down a little bit. Okay, whatever. Here, no, one more. I want my equivalent. I can't do it. You know what I'll do? Maybe I'll do it upside down. I can't draw the curve, y'all. Can't do it. Okay, whatever. I gotta go with it at this point. Okay. This is supposed to be my halfway point, okay? So I would like for you to tell me what is equal. And I want to say that the pH is equal to the pKb. Pretty sure I'm right there, okay? No, that would be the POH. It's still the halfway point. I'm not getting into all that. I can't even right now. I just totally lost it. So what do we know here? We know that it would be a KB, wouldn't it? We know that here we have an excess. At this point, we have all NH3, right? As we add hydrogen, we start to form NH4. At the halfway point, the ammonium is equal to the ammonia is equal to the ammonium, right? Beyond that, anywhere beyond that, the ammonium is greater than the ammonia, right? And prior to that, the ammonia was, greater than the ammonium. Okay, at the halfway point, they're equal. At this point, we've got less base, more conjugate acid. Okay, down here is supposed to be our equivalence point. All right, so I want you to think about that. At the equivalence point, there is no excess of H or OH, and all NH3 has been removed, right? All of our base is gone. We had a lot of base. We still had more base. We had base equal to conjugate acid. We had more conjugate acid. We have no base. Therefore, we only have the conjugate acid of the weak base present. And just as in the strong acid or weak acid, strong base titration, this conjugate acid will participate, if you will, in equilibrium with water, right? So when we've got a bunch of ammonium ions sitting in our solution, well, the water is sitting in our water. There's going to be a slight or you might like to see it simply like this. Remember, ammonium is a weak acid, right? The ammonium ion is a weak acid. So as it's sitting there at the equivalence point in water, it will dissociate to some extent, causing an increase in the pH. No, actually, that's a decrease, right? pH going down with the excess of hydrogen ions. Therefore, a decrease in the pH. Okay. The thing is, guys, you've got to be able to explain that. You know, why is the pH less than 7 when a weak base is titrated with a strong acid, right? It's because at the equivalence point, the only species present is the weak acid that then dissociates to produce an excess of hydrogen ions. And we see a decrease in the pH. So if the titration curve shows a pH at the equivalence point that is less than 7, then we know our situation must be a strong acid and a weak base, right? The weak base being the titrant or analyte. Okay? Okay. I think that's pretty good if you understand that. So go back up here. I put a lot of questions, and I love these questions, but we'll look at, I'm not going to look at those right now. This is all conceptual today. Notice in review, strong acid, strong base, pH of 7. The net ionic equation here is H plus OH yields water. And all of our conjugates are weak. So there's no equilibrium concern about our conjugate acids or bases because they are conjugates of strong acids and strong bases. What else could I infer from this? Hold on. Let me see if there's anything. Titration of 25 milliliters of 0.1 molar HCl with 0.1 molar NaOH. So I see that it took me 25 milliliters, right? So I could read this graph and realize that it took me 25 milliliters of 0.1 molar NaOH. And I could determine my moles of OH. Let's do this into this box. Moles of OH. And I could equate that to moles of H. And I could equate that to the concentration of the strong acid. Right? So a titration curve, if that wasn't given to me, right? All right, let's look at the next one. We've got the weak acid, strong base. So I'll go strong base, equivalent should be greater than 7. And in fact, oops, you see that it is a little bit greater than 7. Right? Doesn't have to be a lot, but not 7. We know that this is our halfway point. This is our optimal buffer zone. That's the case with the other one too. Why is it an optimal buffer zone? Because our conjugate acid and our weak acid and our conjugate base are in 1-to-1 ratio. pH equals pKa. We have both present. We can absorb both acids and bases without our pH changing very much, right? It's flat here. pH isn't changing very much. I could, once again, I see that 25 milliliters of a certain concentration of hydroxide was added, right? I could start doing some calculations. Strong acid. Yeah, we do not need to deal with this here, okay? but you see the strong acid, weak base, the concentration here is less than. Sorry. Sorry. I was just wondering why there wasn't a basic one, right? That's okay. It doesn't matter. Here is our pH equals pKa, or the pOH equals the pKb, optimal buffer zone, yada, 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 yada. Okay. Thank you all. Last day of school for 2020.